Welcome to Chapter 7, Timers and Programmable Logic Controllers. In this lecture, we'll learn how timers control the timing of events inside a PLC program. You'll see how they delay, maintain, and retain actions in automation systems. We'll focus on three key types: on-delay, off-delay, and retentive on-delay time. Timers allow us to delay the start of a motor, keep a light on for a few seconds after a button is pressed, or make sure one operation finishes before another begins. Without timers, automation systems would act instantly, with no coordination or safety delays. Every timer instruction has three key quantities: time base, preset value, and accumulated value. The time base is the unit of time the timer uses to measure an event. For example, 1 millisecond, 10 milliseconds, 100 milliseconds, or 1 second. A smaller time base gives greater accuracy. In RS Logic's 5,000 controllers, the time base is 1 millisecond. The preset value sets how long the timer will run. Total time equals the preset multiplied by the time base. For instance, a preset of 10,000 with a 1 millisecond base equals 10 seconds. The accumulated value shows how much time has passed since timing began. When the accumulated value reaches the preset, the timer is complete. The timer block has two main input conditions: control and reset. The control input starts the timing operation. When this input is true, or when power is applied, the timer begins to count. If power is removed or the control input goes false, the timer immediately stops timing. An on-delay timer is used when you want to program delay before an instruction becomes true. When the rung containing the timer turns on, the timing period begins. After the preset time has elapsed, the timer's output becomes true. This is why it's called an on-delay timer. The length of the delay is set by the preset value, and many PLCs also let you adjust the time base or resolutio. In example, a motor starts 5 seconds after pressing the start button. If you release the button early, it never starts. In Allen Bradley RS Logic's 500, all timer data is stored in file number 4, which is called a timer file. Each timer in this file is known as a timer element, and each element is made up of 3 16-bit words. For example, the address T4:2 refers to T4, which means timer file 4, and :2, which identifies timer element number 2. Each timer element has several key addresses associated with it. T4:2/DN refers to the done bit. It turns on when the timer reaches its preset value. T4:2/TT is the timer timing bit. It stays on while the timer is counting. And T4:2/EN is the enable bit. It's true whenever the timer rung is energized. Inside the timer file, word 0 contains the control bits: enable, timing, and done. Word 1 stores the preset value, and word 2 stores the accumulated value. In short, each timer element in RS Logic's 500 neatly combines the timer's control status, preset time, and elapsed time in one organized data structure. This diagram shows how an on-delay timer works in a programmable logic controller ladder program. On the left side, we see the input circuit. When input A is pressed, power flows into the rung that contains the timer instruction. In the middle, we see the blue timer block labeled T4:0. This is a timer on delay instruction, often called TON. It means the output will not turn on right away. Instead, it will wait for a preset time before becoming true. Below the timer, we can see 3 important values. The time base is 1 second. The preset is 10 seconds. And the accumulated value starts at 0 and increases while the timer is counting. Here's what happens step by step. When input A turns on, the timer begins counting time. While it's timing, 2 internal bits become true: the enable bit, labeled T4:0EN, and the timer timing bit, labeled T4:0TT. These stay on as long as the timer rung has power. When the accumulated value reaches the preset value of 100 seconds, the done bit, labeled T4:0DN, turns on. That signals the end of the timing period. On the right side of the diagram, you can see 3 outputs connected to these bits. When the enable bit is on, output B turns on. When the timer timing bit is on, output C turns on. And when the done bit is on, output D turns on. In this example, each output could control a light. The green light shows the timer is enabled. The red light shows the timer is timing. And the yellow light shows the timer has finished. This example demonstrates how the three internal status bits, enable, timer timing, and done, can be used to control different outputs during the timing cycle. Now let's simulate this circuit in Logix Pro. First, we click the timer table and select the T4 timer output for T2:0. We then download our code to the PLC. Place our PLC in run mode. Select the I1/0 input, and the counter begins counting up to 100 seconds in increments of 0.1 seconds. Notice while it's counting, output B and C are on and output D is off. Once it reaches 100, output D comes on and output C goes off. This slide shows how an off-delay timer works in a programmable logic controller. On the left, we see the input circuit. The input device, labeled S1, is a normally open switch connected to the timer instruction T4:3 in the center. In the middle, the blue block represents the timer off-delay instruction. Its time base is 0.1 seconds, and the preset value is 100. That means the total delay time is 10 seconds, calculated as the time base multiplied by the preset value. If this were set for 15 seconds, the preset would be 150. Now let's look at how it works. When the switch is first closed, the timer's done bit, labeled T4:3/DN, immediately turns true. This energizes the pilot light on the right, labeled PL, meaning the lamp turns on right away. When the switch is opened, the timer begins counting. The pilot light stays on during this timing period. Once the accumulated value reaches the preset time, the done bit turns off, and the lamp turns off as well. That's why this type of timer is called an off-delay timer. It delays turning off the output. If the switch is closed again before the timer finishes counting, the timing stops immediately and the accumulated time resets to 0. In short, the TOF timer keeps the output on for a fixed period after the input turns off. This is useful for applications like keeping a fan running after a heater shuts down or maintaining lights on briefly after a process stops. A retentive timer accumulates time whenever the device receives power, and it maintains the current time should power be removed from the device. When the timer accumulates time equal to its preset value, the contacts of the device change state. Loss of power to the timer after reaching its preset value does not affect the state of the contacts. This slide shows how a retentive on-delay timer, or RTO, works in a programmable logic controller ladder program. On the left, we have two push buttons, labeled PB1 and PB2. PB1 is the time start button. PB2 is the reset button. In the middle section, we see the ladder logic program. The RTO instruction, shown in blue, is labeled T4:2. It has a time base of 1 second and a preset value of 9 seconds. That means the timer will reach its done condition after 9 seconds of accumulated runtime. Here's how it operates. When PB1 is pressed, the timer starts counting. While it's timing, the enable bit is true and the accumulated value increases once per second. If the button is released before the timer reaches 9 seconds, the timer pauses, but the accumulated time is retained. When PB1 is pressed again, the timer starts counting from where it left off, not from 0. That's what makes this a retentive timer. Once the accumulated time equals the preset value, the done bit, labeled T4:2/DN, turns on. On the bottom rung, the done bit is used to energize the pilot light, labeled PL, on the right side of the diagram. This light turns on once the total runtime reaches 9 seconds, even if the timing happens in multiple intervals. To reset the timer, PB2 must be pressed. This activates the reset instruction, labeled T4:2/RES, which clears the accumulated value back to 0. In summary, the retentive on-delay timer keeps track of elapsed time even when the input turns off, and it only resets when a separate reset command is given. It's ideal for applications where total runtime must be accumulated, such as tracking machine operation hours or cumulative warm-up cycles. So to summarize, there are three main types of PLC timers. The on-delay timer delays, turning on an output after the input turns true. It resets to 0 when the input turns off. The off-delay timer delays, turning off an output after the input turns false. It keeps the output on for the preset time before de-energizing. The retentive on-delay timer accumulates time across multiple cycles and only resets when a separate reset instruction is activated. In short, on-delay timers delay turning on, off-delay timers delay turning off, and retentive timers keep time until it's reset. In the next lecture, we will discuss the various types of PLC counters.